Okay, supplemental video for 7.2. I just threw together a few problems that are like some of the ones in the 7.2 homework, and I'll just go through. We'll sketch some pictures at least. I won't necessarily solve the whole thing, but at least you can get an idea what the pictures will look like. And anyway, it's just more examples of that kind of stuff. So, first one here. A plane with a heading of 168 degrees and a speed of 333. And then we have wind with a speed and a heading as well. And we're going to see what the actual direction and speed of the plane is. All right, so first off, how do we draw a heading of 168 degrees? All right, so this will be the beginning of the plane vector, and we need our line that goes straight north. And 168. All right, remember, for headings, straight north, rotate clockwise. All right, anywhere from 0 to 360 degrees. So here we have, I completely lost my mouse. Where'd it go? Oop, there it is. Okay. 168 degrees. So again, 180 would be straight south. 168 will come up a little short, something like this. All right, so here's 168 degrees and a speed of 333. So that's a vector. I don't usually draw those arrowheads because it just makes a bigger mess of the picture. There's the vector for the plane, that direction, that length. Now the wind we're going to tack onto the end of this vector. So the end of the plane vector will be the beginning of the wind vector. So I put a north line there because we're going to measure the heading of the wind from there. And the wind's heading is 123 degrees. So 90 would be straight east, 123, more like that-ish. All right, and this angle is 123. And the length of the vector for the wind is 47. Now, true course of the plane would come from connecting beginning to the end, finding that length, and figuring out what this angle is, right? From the dashed line just to the top line of the triangle. Okay, so what we need to do, well, if I redraw a little bit of this triangle here, we got 47, we got 333. This comes on down. Boy, that is terrible. We need an angle in the triangle. All right, and at this spot right here, which I'll just call B, we know from the dash line to the 47 side, that's 123. So if we knew this little bit right in here, we could add that to 123 and we'd have it. Now here's where our parallels come in. So dash line, those are parallel. And we have dash line, the 333 line, and then a dash line, where this is the 168 that we labeled in the picture. So if that's 168, you can actually figure out what that is. Two different ways. One, you can remember, well, we're made with the same line, and we're between the parallels. We're obviously not equal, but then we have to add up to 180, so that would make this 12 degrees. Or if this dash line continued down, 168, this would have to be 12 because we're making a straight line. And then the 12 I already wrote is an alternate interior angle for that 12 degrees that I wrote second. So either way, you're going to get a 12 in there. So in my terrible picture here, 12 degrees, which means angle B in our picture is 123 right here, and then plus 12, so we get 135. All right, so what that makes for this situation then is SAS, and first thing in SAS is to find the missing side, so you would do that, and that would be the actual speed of the plane. Now the true direction, the actual direction it's moving, well, if I call this A, you would want skinny little angle A in the triangle. And from there, well, we know it's 168 to the 333 side. So you could just subtract whatever angle A is to get the actual heading in then. So 168 minus angle A would be the actual heading. All right. Now, if these were switched around, so slight modification, what if this was the 123 and this was the 168, right? How would that change? All right, well, dash line. Now the plane is pointing in the direction 123, so we get a long line there, 333, and this would be our 123 degrees. Then on the end of that goes our wind vector again, and that would be the 168 degrees. So here's 168, and this would be our 47. And we would be trying to find the length and direction of that vector. Now, you'd have to work through some things and figure out what this angle is. You'd have side angle side. You can use that to get the missing side. And then you would still find the skinny angle A, but in this case you would be adding it on to the 123 because 333 is the actual, or sorry, the direction the plane is pointing, all right? But the actual direction is from the bottom line in this particular case. Okay. Okay, that's that one. I don't know if I can erase. Let's erase. I don't know if I can do this easily at all, or if I can even just do a whole bunch of this. Ooh, there we go. Okay. So getting rid of, oh, it's a lot. All of this stuff. Hang on. Oh, nope, that's as far back as it's gonna go. Okie dokie. I'm gonna draw some pictures for this next one. And then we'll talk about that last one as well. This is not an efficient method of clearing the screen, but I'm afraid if I say let's do a new one, I'm gonna lose all my text and whatnot. Okay, anyway, good enough. So here we go. Plane. Heading of 60 degrees at 440. Let's get a little thicker than that. All right, 60 degrees is this direction. 440 miles an hour. The actual direction and speed is 55 degrees, 410. So now this would be 60 degrees. So the actual speed is at 55 degrees. So straight north, rotate only 55 degrees. And you get 410, like, oops, not degrees, just 410. And this is 55 degrees. All right, so then the wind, well, we'd like to know what direction or how long that wind vector is. So remember, so this is the direction the plane is pointing. So the wind must be blowing this direction to give us the actual direction and speed of the plane. All right, so let me just erase. Let me try to erase this guy. There we go. So in terms of the direction the wind is blowing, well, this is the start of the wind vector. This is the end of the wind vector, which means at the beginning of that vector, we need to put in a north line. And what we'd like to know is what this angle is right there. And if we can figure out that angle, then the actual heading of the wind, the speed of the wind will be the length of that side. The actual heading would be this guy from straight north all the way, oops, I did not make that go far enough, all the way to the wind vector. So on my crude drawing, it looks like it's going to be northwest-ish for the wind, so something like 315 degrees or that kind of ballpark. Now actually getting there, well, you can see our triangle. We have two sides, 410 and 440. And the 55 and the 60, easily, if we call this A, angle A is pretty clearly just 5 degrees, the difference between 60 and 55. So this is, again, a side angle side situation. And so law of cosines would give you the length of that short vector of the wind. And then we'd have to work some angle magic to figure out some other things. We know this angle in the triangle. If we figure out, I'm going to call this C and B. If you figure out angle C in the triangle, what else do we know here? There's a lot going on in our picture at the moment. All right, so here's this, and this, and this. So if we can figure out this angle, and we know that this is 60. All right, well, if this is extended down, that means this is 60. And this much we know is 180. And if we know angle C, well, then we can add up 180 plus 60 plus angle C, and that would give us our total heading for the wind all the way around. So in particular, actually, I labeled this guy up here at first. We could figure him out, but we don't need to know him. What we really need is angle C, and then the stuff can get tacked on to that. The 180 plus the 60 here, and then plus angle C. And that would give us our actual heading for the wind. All right, one more different sort of problem, no planes and wind and that sort of stuff. There's a horse problem and a tugboat problem, kind of like this one in 7.2. So, Greg and Jake pull a large rock. Jake with tension in the rope, so force he's applying of 54 pounds, Greg's is 61 pounds, and 19 degrees between them. So if we drew a picture here, kind of look like 61, 54, and 19 degrees between them. And that's what the horse picture kind of looks like in the homework. Here's your rock that's getting pulled. And the inclination is to say, oh, heck, that's side, angle, side. We'll just connect that up there and solve the triangle, and that's great, except, no, that's not how these two forces add up. To add up the forces, okay, well, here's 54. Adding vectors means drawing one and tacking the other one onto the end of it. Or in other words, completing the parallelogram. And the result is what comes all the way across here. All right, so if I were just to draw this onto the end, and this was 61, and then this, like so, is that magnitude is what we're trying to figure out, the length of that side. Well, if you go back to the parallelogram, and I'm going to resketch them just to point at some things. So this is 19 degrees right there. And we also know that, well, these are both 61s. These guys are parallel, and these guys are parallel. And just like we've seen in actually both of the previous problems, 19 degrees actually tells you what this angle is right there. So if the two 61s are parallel, then 19 degrees plus whatever this is has to be 180. And so this angle ends up being 180 minus that, which is 161 degrees. And that matters because when you draw in the diagonal whose length you're trying to get, the 161 is actually the angle in the triangle, not the 19 degrees. So it is a side angle side situation, but it's side, side, and then your angle is this 161, which comes from the 19 degrees that was stated in the problem. And now you can do side, angle, side. And I mean, if you just did this, 54, 61, and you found this length, it's clear that that's way shorter than the other two. So if you have two people pulling on a rock with these forces of 54 and 61, the total force is going to be something bigger than both of those guys, since we're pointing in vaguely the same direction, whereas this line's going to be way shorter. And you get an answer that says the total force is 22 pounds or something crazy, when that's obviously not the case at all. But with this sort of picture, oh yeah, you can see this total force vector is quite long, and those two forces will add up to a greater force than either of them. Okay. There's 3 more examples. I hope those help. It's hard to do these problems without drawing pictures, which is what makes it hard to do over email and whatnot. So hopefully these will help some. Feel free to ask me questions again if you still have them. I did not throw a whole boatload of these on that vectors quiz. That was just a lot of basics of vectors to get through some things. So anyway, that's it.